To take a system at equilibrium and do a Le Chatelier's shift is just more work than the other method. And so the second method that we did is easier. And so what we're going to do with all problems from now on is we're just going to start off resetting the equilibrium. So let's see. Okay, any other questions? No? All right, let's move on to another problem here. We're going to look at 1.0 times 10 to the minus 8 molar HCM. And the Ka value for this is equal to 6.2 times 10 to the minus 10. All right, the method that we've been using so far is the stepwise method. The stepwise method, what I've been doing is I've been starting off with the biggest K, and then just go smaller in each successive step. And so if we have, we're going to have multiple equilibria, so we've got Ka here. And this is an acid solution. So in acid solutions, we just look for hydronium ion contributors. This is a monoprotic acid. And so we just have a Ka1, call it, or just one Ka. And we'll also have Kw. And so there are going to be two hydronium ion contributors to the solution, Ka and Kw. And then we look at the magnitude. Ka is 10 to the minus 10, Kw is 10 to the minus 14. And so we would do Ka first, followed by Kw. Like in 99% of the cases, Kw comes last, but not always. And there's 1% cases where we'll actually have to do something like Kw first. And so let's take a look at some Ka values. Okay, if we look at the Ka values in this table, this is from Appendix D here. Let's take a look for the biggest and the smallest one. So I'm just scanning it here. I see this one's pretty small, 10 to the minus 19. 10 to the minus 19, that's for the HS minus. So something like a sodium hydrogen sulfide have a very small Ka there. Okay, that's about the smallest. It looks like the biggest Ka value is 10 to the minus 1 here. There's 1.6 times 10 to the minus 1. 3, this is bigger here. 3.0 times 10 to the minus 1. 3.0 times 10 to the minus 1 is trichloroacetic acid. Trichloroacetic acid is pretty acidic. Have the inductive effect. Having the 3 chlorines there is going to just increase the magnitude of the inductive effect. But that looks like it. Unless, let's see, what's this? This is a strong acid. What does that mean? Strong acid. I want a number here, but I don't have a number. Instead, I just have strong acid. Selenic acid also is a strong acid. Selenic acid is not very common, so you're going to have to memorize this one. It's a strong acid as well. There are others, they aren't in this chart. The other strong acids aren't in this chart because it just say the same thing, strong acids. These happen to be dichroic, so that's why we put them in here. But what does this mean, strong acid? Very big, yeah, very large. It means it's very large. Maybe not infinite, but pretty large. And so we aren't actually going to put a number. We're just going to assume it goes to completion. So that's what those mean. And so we look, and so in most cases, Ka is going to be bigger than Kw, so we do Ka first. However, if we had something like Hs minus, we would do Kw first. Kw is bigger, so we would do that. And so that tells us what sequence we're going to go. And so in this case, we're going to do HCN first. HCN should be the major contributor of hydronium, it looks like, because of this. And so we do it in steps. And so we'll just say step 1 here will be to figure out how much hydronium we're going to get from HCN. That would just be the hydrolysis here. HCl plus cyanide. All right. Initial concentration, we assume that no collisions have taken place between HCN and water. And so we just have 1.0 times 10 to the minus 8 moles of molecules of HCN. And those will collide with water during the change here. And so initially it's all intact. We're going to lose some, minus X, plus X plus X. And so at equilibrium we'll have 1.0 times 10 to the minus 8 minus X molar and X molar and X molar here. All right, so Ka for this will be equal to the hydronium times the cyanide divided by the HCN, the HCN molecules. So that's X times X, which gives us X squared, divided by 1.0 times 10 to the minus 8 minus X. All right, although, this is not that hard, it's a quadratic equation. It doesn't take long to try the simplifying assumption. And so we go ahead and try the simplifying assumption. Simplifying assumption would be just X is much smaller than 1.0 times 10 to the minus 8. And so X has got to be really, really small, but we'll just try it. And so X squared over 1.0 times 10 to the minus 8 minus X is just 1.0 times 10 to the minus 8. And so let's solve this for X. That's 6.2 times 10 to the minus 10 times 1 times 10 to the minus 8. And take the square root of that. I get 5.53 times 10 to the minus 8, 6, 7, 8, times 10 to the minus 8. All right, then we have to check our assumption. Did anybody else get this? Well, let's just go ahead and check our assumption by doing the percent change. So the change here is this, X, over the original. 1 times 10 to the minus 8, so I'm going to just take that divided by 1 times 10 to the minus 8 equals that times 100. 553% change. Double check the number. Did anybody else get this number? No? What did you get, Sabrina?
Oh, I was just like reading into it.
Oh, okay. Let me check this here. Oh, you know what? I think I screwed up. 6.2 times 10 to the minus 10 times 1 times 10 to the minus 8. That and then take the square root. Oh yeah, you're right. Yeah, actually I must have made an error here because let me read this. 3, 6, 7, 8, 9. 2.3 0.48 times 10 to the minus 9. Didn't anybody get that? Yeah. All right. And so let's do the percent change again. So this is going to be divided by 1 times 10 to the minus 8 times 100. 24, oh, actually, it comes out to 24.89%. 24.89, still too big. And so that wasn't a terrible waste of time, because if it would have worked, it would have saved us a lot of time, but we can't use it. We're going to have to use the quadratic. But fortunately, this one's easy to get into quadratic form, so let's go ahead and get it in quadratic form. It's going to be x squared plus 6.2 times 10 to the minus 10x, like minus 1.0 times 10 to the minus 8, is that right? Is equal to 0. Let's try this in the quadratic solver here. So A is 1, B is 6.2 times 10 to the minus 10, and C is 1 times 10 to the minus 8, is that right?
It would be 6.2 times 10 to the negative 18. Which you're multiplying it by.
Oh yeah, it's going to be 6.2 times 10 to the negative 18 here, because here this would have clued us in, because if I solve this here with the wrong number, I'm going to get something, well, a negative number here, but also I'm going to get this one, which is quadruple 0, 9, 9. And so if I have quadruple 0, 9, 9, this is going to make this number negative. And so definitely something was wrong with my equation, because solving it for the quadratic gives us a totally nonsensical answer. So this is going to be 6.2 times 10 to the minus 18. Let's see if that gives us a reasonable answer here. And so we're going to have negative 6.2 times 10 to the negative 18. Let's solve that. And so this is going to give me 2.199 times 10 to the minus 9. Well, is that, how far off is that? You know, if we use the quadratic, we get about 2.19 times 10 to the minus 9. If we use the simplifying assumption, we got 2.48. There's about 0.3 difference. Well, 0.3, it's going to be about a 12% difference between the two numbers. And so, which is, you know, it's not terrible. I mean, it's close, but obviously with the quadratic, we're going to be much, much closer. In fact, we should get an accurate answer here. And so let's go ahead and figure out how much HCN reacted. So here we got 1.0 times 10 to the minus 8. It's going to be minus 2.19 times 10 to the minus 9. And so I'm going to convert that. I'm going to change it to 0.219 times 10 to the minus 8. Is that right? Make this number bigger, I'm going to make the quotient smaller. That's right. And so this is going to give me 0.781 times 10 to the minus 8. And so it looks like I have about 78% remaining and about 22% hydrolyzing. So 22% of the HCN molecules have reacted in this case. So that's the percent change of the percent reaction. Like we you know, here, over here we calculated 24, 25%. So that's off. It's off a little bit too much. So should have been closer to 22% reaction. And so the hydronium over here is going to just be 2.19 times 10 to the minus 9 molar. And the cyanide is the same, 2.19 times 10 to the minus 9 molar. All right, so this is the hydronium that's produced in step 1. And I'm going to move on to this. There's also going to be hydronium produced in step 2. Step 2 is the KW. So the KW is this H2O liquid plus H2O liquid. This is going to give us hydronium. That's hydroxide. Now, it's important, normally how much hydronium and hydroxide is produced here. And so getting back to Sabrina's question about number 40. In number 40, the first way I approached it is via Le Chatelier's approach. And so let me just do that as an aside because I give up on that approach over here. And so if I were to do this problem like I did problem number 40, this is how my step 2 would look. The way I did problem number 40 the first way is taking a system at equilibrium and then perturbing it. And so the system that would have been at equilibrium is water. We know the collision's already happening. And we know that it's 1.0 times 10 to the minus 7 molar and 1.0 times 10 to the minus 7 molar here. That's the initial from water. H2O is liquid. But now we're going to perturb it because what we're going to do is we're going to take this hydronium that we just generated in step 1 and add it to the water. And so I need to take the hydronium over there, 2.19 times 10 to the minus 9. And then add the 2. So if I convert this to 10 to the minus 7, I'm going to move it over 2 decimals. So I'm going to have 1.0219 times 10 to the minus 7 molar. And so if the hydronium concentration increases, then Le Chatelier's principle says, well, if the concentration of the product increases, then I'm no longer at the equilibrium ratio here. It's got to shift to the left. Right? If this shifts to the left, then this is my new initial, the perturbed initial. This is a perturbation from HCN. Then the change is going to be minus X molar, minus X molar. And then I solve it. But I don't like doing it this way. I don't like doing it this way. The way I like to do it is I just like to reset it. I like to imagine that none of the H2Os reacted. And then what I'm going to do is I'm going to introduce the hydronium right at the start because this is the hydronium that comes from step 1. This hydronium in the next chapter we call a common ion. This is a common ion in both of these equilibria. In fact, this is the only common ion between both these equilibria. Both these equilibria share hydronium in common. And so we have to compensate, because both of them have hydronium, and I'm going to add that there. And so what I say is nothing has hydrolyzed here. And so the water hasn't collided with the water. Obviously the water, you can't stop the water from colliding, but we can do this for our calculation purposes and not just move all the molecules back to the left. And so the second way that we did problem number 40 is this way, where we just reset the second ice table back to the left, and we start off with no hydrolysis. Now the change is it going to be plus 10 to the minus 7 molar, plus 10 to the minus 7 molar? No, it's not. It's not going to be plus 10 to the minus 7 molar and plus 10 to the minus 7 molar because we don't need as much. In a common ion type problem like this, since we already have some existing here, the plus X is going to be a lot smaller because we don't need as much to equal KW. In other words, it's kind of Le Chatelier's principle in action, but it's preventing the forward reaction from occurring to its full extent. So this is a common mistake. A common mistake is people will say plus 1.0 times 10 to the minus 7 molar, plus 1.0 times 10 to the minus 7 molar. But if they do that, they have too much. It's not going to be at equilibrium anymore, and it's got to shift the other way. And so that's what we're going to calculate. We're not going to bother adding plus 10 to the minus 7, plus 10 to the minus 7, and then doing a Le Chatelier shift backwards. We're just going to do one calculation, and that's it. And so at equilibrium, we're just going to have 2.19 times 10 times 10 to the minus 9 plus x molar, and then x molar here. So this is Kw. Kw is just the hydronium, this is the hydroxide. And that's going to be 2.19 times 10 to the minus 9 plus x times x. All right, here, since it doesn't take very long to do the simplifying assumption, I'm just going to go ahead and do it again. 2.19, we'll just use the simplifying assumption. That is, this is just a drop of water out of the swimming pool. Well, this is a very small swimming pool, so this must be a very small drop. But anyway, we'll do 2.19 times 10 to the minus 9 plus x is just 2.19 times 10 to the minus 9. And then x stays, because x is compared to 0. Anything compared to 0 is significant. And so with the simplifying assumption, then we can solve for x quite rapidly. And so let's see what it comes out to. That's going to be 1 times 10 to the minus 14 divided by 2.19 times 10 to the minus 9. 2.19 times 10 to the minus 9. 4.56. 4.56 times 10 to the 6 is 10 to the minus 6. Then we calculate the percent change. Percent change is 4.56 times 10 to the minus 6 divided by the original, which is 2.19 times 10 to the minus 9 times 100. So let's go ahead and divide that by 2.19 times 10 to the negative 9 times 100. And it comes out to 208,502%. Do you think this answer is going to be close? No. And so, unfortunately, the simplifying assumption failed. Sometimes you can tell it's going to fail just by looking at the numbers. Typically, what we want for the simplifying assumption to succeed is we want a large initial. Well, in this case, we have a pretty small initial. And then we want a very small k. Well, we do have a very small k. Now, Petrucci comes up with a ratio of k over the concentration of the k. If it's a 1,000-fold difference, then maybe it'll work. The bigger the difference, the better for that. But anyway, we aren't going to look at it just yet. What we're going to do is we're just going to just solve this using quadratic. Fortunately, this is very easy given in quadratic form. I'm less likely to make mistakes here. 2.19 times 10 to the minus 9x minus 1.0 times 10 to the minus 14 is equal to 0. So let's go ahead and plug that into your calculator here, or whatever you got. 2.19 times 10 to the minus 9. And then negative 1 times 10 to the minus 14. 14. Solve it. All right, the negative x is not going to work. This is times 10 to the minus 8. So what we got here, 9.89 x is equal to 9.89 times 10 to the minus 8. All right, that's using the quadratic to solve it. So we don't have to justify anything. This is going to be 2.19 times 10 to the minus 9. And so I'm going to convert that to 10 to the minus 9. Make that submit. So this is going to be plus 98.9 times 10 to the minus 9. And so this is going to give me 101.09 times 10 to the minus 9 molar. That's for the hydronium. And for the hydroxide, I'm going to just get 9.89 times 10 to the minus 8 molar. Actually, what I should do, which I didn't do on step one, is I should double check. I should have double checked my calculations. And so, let's go ahead and double check this. Since I forgot, I'm going to go back to step one. I forgot to double check this. And so let's go ahead and double check here. And the double check is just to make sure that this is the correct equilibrium ratio. So let's go ahead and take the products of the reactants. So this is going to be 2.19 times 10 to the minus 9 squared. So 2.19 times 10 to the minus 9 squared divided by 0.781 times 10 to the minus 8. 0.781 times 10 to the minus 8. Wow, I think maybe, did I screw this up? Let's try that again. 2.19 times 10 to the minus 9 squared divided by 0.781 times 10 to the minus 8. Okay, I did screw it up. So came out. K, I get 6.14 times 10 to the minus 10 to the minus 10. Am I close? I erased it. What was it? Oh, I didn't erase it. It's here. 6.2. I'm at 6.14. What do you think? Is that acceptable? It's off a little, isn't it? Why do you think it's off? Maybe I made another math error. It happens. So I could double check the numbers, or, this type of stuff happens quite often. It happens. I'll tell you what happened. What do you think happened? I'll tell you what happened. What happened was round-off error. Let me tell you. This is why I carry a lot more digits, because I don't want to have to think about this. I don't want to have to think, did I make some stupid error where I got the numbers mixed up or something like that? Or or is this just a simple round-off error, which we're allowed? A round-off error we're allowed because we aren't allowed that many sig figs for this calculation. And so it often will save you time writing the extra digits versus worrying about this, especially if this number comes up. Let's say if this number came out to 6.0, it's supposed to be 6.2. Is that close enough? Or if it came out to 5.9. If it came out to 5.9 times 10 to the minus 10, it's supposed to be 6.2, then you got to start worrying. There's probably some kind of math error in there, not just a round-off error. And so the question is that difference, it's a slight difference, 6.1 versus 6.2, due to round-off, or is it due to I just maybe wrote down the wrong number or copied something off? Something's off here. Okay, so to save you time in the long run, I just write extra. Let's double check this one though. And so that one's close. So this one is just hydronium times a hydroxide. So hydronium times a hydroxide, let's see what it comes out to. So I get 101.09 times 10 to the minus 9 times 9.89 times 10 to the minus 8. All right, this one comes out. This one comes out right on. 1.000 times 10 to the minus 14. So we're good here. This one, there's no question about it. And so I must have gotten the numbers correct. And so with the double check for the K, this is good. And we'll just go ahead and take this as good here. And so the two Ks check out. So am I confident now? Can I be confident with regards to my calculation? It looks like I didn't make any errors, other than rounding, which is going to happen anyway. Does it look good? Well, this is a little different because this is what we did in chapter 15. In chapter 15, we look at just single equilibrium. The single equilibrium, you know, then we double check it. In chapter 16, we look at multiple equilibria. In multiple equilibria, we have to do one more check. Do you know what that one more check is? And this is something we didn't do yet because we didn't have to. But the one more check is this. In this mixture, I have HCN and water. Right? HCN and water in this mixture. And if you look at the common ion is hydronium. You know, the common ion in both these equilibria is hydronium. On the left, I should have a hydronium of 2.19 times 10 to the minus 9. On the right, I should have a hydronium of 101. So what is it? Is it 2.2 or is it 101? Well, it has to be 2.2 for the left equilibrium. So maybe what I'll do is on the left side of the liquid, I'll make the hydronium 2.2 times 10 to the minus 9. And then on the right side of the liquid, I'll make it 101. Is that doable? Like what I want to do is I just want to divide it right in the middle here and have it 2.2 on this side and then 101 on this side. Doable? No, impossible. In fact, this is a beaker, this mixture, and there's only one hydronium ion concentration in here. There can only be one hydronium ion. How can you have two hydronium ion concentrations in a single solution? You can't. And so which is the hydronium ion concentration going to be in this beaker? Is it going to be the left one or the right one? Well, it's going to be neither. It's going to be neither because this is an impossible situation. This is an impossible situation because what's going to happen is this. There are two ways of thinking about it. We can't have two separate hydroniums. The other way of thinking about it is Le Chatelier's principle. What Le Chatelier's principle says is after we figure out the equilibrium here, we've just screwed up the equilibrium here. So we just got this equilibrium, nice, and now we just add a whole bunch more hydronium, which means the first equilibrium is no longer going to be an equilibrium. And so what's going to happen is Le Chatelier's principle is going to say that, well, if I started off with 2.2 and now I'm at 101, I better fix that. And so if this goes from 2.2 to 101, it's got to shift backwards. And then I shift this backwards doing Le Chatelier's, like problem number 40, part 1, the first way we solved it. I could do that, but what's going to happen is if this shifts backwards, that's going to screw up my second equilibrium. And so what I end up with is an endless loop. I fix one, screw up the other, fix the other, screw up the first one. And so I get this endless loop. I can't solve this way. I can't solve this way, but you know, didn't I use stepwise for the previous two problems? I used stepwise for the last problem, but what was unique about that last problem was that the common ion, there were multiple common ions, did the concentration change significantly in going from step to step? No, the concentration was about the same. It was, what was it, 0.0045 or something, or roughly? You recall that? Concentrations didn't change. Except the problem I did before that, the HCl problem. Do you remember the HCl problem? You know, we ran into this exact same scenario before, but you know, I didn't factor this in. The first multiple equilibrium problem we did was HCl. And do you have the numbers for that? Did anybody write it down? The numbers for the HCl? Think back to 1.0 times 10 minus 8 molar HCl. And so, you know, this is two equilibria. HCl plus water was the first one. You start off with the biggest K. when we did this. This gave us hydronium chloride. And so initially we started off with 1.0 times 10 minus 8 molar. The water is liquid, 0, and 0. And then at equilibrium we had 0, and then 1.0 times 10 minus 8 molar, and then 1.0 times 10 minus 8 molar. Now hydronium is a common ion with Kw, so we go to H2O liquid plus H2O liquid here. And we have hydronium produced in hydroxide. So this is going to go down here. And what did we end up with at the end? So initially we had 1.0 times 10 minus 8. We reset this, like, problem number 40, the second play we did. And at the end, what did we have? Can somebody give me the final equilibrium hydronium? Well, I'll just write. It was like 10.5 times 10 to the minus 8 molar. And so we went from about 1.0 to about 10.5. We added about 9.5. So we added about 95% more hydronium in step 2 here, right? And so all of a sudden we have a big bump in the hydronium. So it goes from 1 to 10, which means this. And we double check this one. Remember, we double check this one. This one checks out, but if we increase the hydronium significantly, then that's going to perturb the step 1. You see that? And so, did I screw that up earlier when we did this calculation? It turned out I didn't screw it up because this does not perturb step 1. The reason it doesn't perturb step 1 is, yeah, that's a huge increase. So Le Chatelier's principle says this should shift back. But what do we know about strong acids like this? What's the K value for strong acids? Very large. And so what that means is this. We treat this as a one-way reaction. Another way of thinking about this is this. Let's say I wanted to lower the pH, or not lower. Let's say I want to increase the pH. That is, I want to make this less acidic. I want to neutralize some of this hydronium. Could I add a chloride, like sodium chloride? If I add sodium chloride, Le Chatelier's principle says if I add chloride and increase the chloride concentration, it should shift it to the left, thereby increasing the pH and decreasing the hydronium. And so, I could just use sodium chloride as an antacid. Would that work? No, it doesn't work because what's K for strong acid? Very large. It's going to go forward. And so even if I increase the hydronium, it doesn't shift it back. It's one way. Because strong acid. The difference here is that, is HCN a strong acid? No, HCN is a weak acid. So weak acid, this is going to be susceptible to Le Chatelier's. Strong acids are not. Strong acids and strong bases is one way. All right, and so what we have is this endless loop. That is, we cannot solve it. By stepwise. In fact, whenever we have multiple equilibria with common ion, we always have to make sure that the equilibrium concentrations, like the hydronium here and the hydronium here, have to match. In other words, the hydronium ion concentration has to simultaneously satisfy both equilibria. Simultaneously satisfy both equilibria. And therefore, rather than using the stepwise method, You know, what we're going to do is we're going to do the proper method. This is the proper method is what we should do for all multiple equilibria, because all multiple equilibria involving common ions have to be simultaneously consistent. So we call this the simultaneous method here, or I call this. I mean, I don't think Petrucci calls it anything. He just calls it another problem-solving method. But this is the other major method that we're going to use. And what we got to do is we got to make sure that both equilibria are consistent with each other. And the only way to make sure that both equilibria are consistent with each other are to solve them simultaneously together. And so it doesn't matter which one I write here. I'm just going to write HCN plus water. Because what we're going to do is we're going to solve these simultaneously. And this is going to be HCO plus sign out here. At the same time, I'm going to solve the water equilibrium, H2O. So we got H2O liquid plus H2O liquid. This is going to yield hydronium and hydroxide. So what I don't want to do is I don't want to solve one and then solve the other. I want to solve both together. And so solving both together, I have to figure out how we're going to do this. And so I'm not going to put in the numbers here because your book doesn't do this. Yeah, I'm going to just say HCN initial. The HCN initial is this, 1.0 times 10 minus 8 molar. That's my HCN initial. Water is a pure liquid. Over here, water is pure liquid, water is a pure liquid. I've got plenty of water. Okay, now what do I do about my hydronium? In a normal stepwise approach, I have 0 and 0 because nothing. I don't allow any collisions to occur here. And so it should be 0 and 0. And then if it's 0 and 0, then I figure out how much hydronium is produced here, and then I introduce it over here. Well, what we're going to do is we're going to do the simultaneous approach. The simultaneous approach means that I have common ion here. And that means that this is not 0. There's another producer of hydronium. What is the other producer? Well, that one over there. And so that means I'm going to have hydronium in here to begin with. And where did that hydronium come from? That came from KW, water. But what I'll say is I don't have any cyanide. So, basically I haven't produced any hydronium from HCN yet. So I'm going to just have 0 molar cyanide here. All right, now I go over here and I go, okay, normally this is 0 and 0 because we reset it. We don't do the 10 to the minus 7, 10 to the minus 7. Just start out at 0 and 0. But again, I got to think this is a common ion, and I have another hydronium ion producer. The other hydronium ion producer is HCN. And so I'm going to have some hydronium here from HCN that's going to be present here. And having that present there is going to, have this Le Chatelier type, inhibition and further reaction. So both of these are going to have common ion. Do you see that? This is how we're going to solve it simultaneously. Versus, in stepwise, this would have been 0, and then we would have added or put the common ion over there. And so for simultaneous, we have to start with the common ion from the other species. And so here, this is just going to be minus X molar, plus X molar, and plus X molar. And so X is going to be smaller for HCN than what we calculated in the previous calculation. It's going to be smaller because we got some hydronium there already from the water. And so here we're going to have HCN initial minus X. Over here, this is going to be the hydronium from water. This is going to be the hydronium from water plus X. And this is going to be X. Okay, we'll go over to this table. So water is a liquid. Here, I don't want to use X again. What should I use instead of X? Maybe I'll just use Y. And so I'm going to get some additional hydronium from water, which I'll call Y. And so at equilibrium, I'm going to have the hydronium from HCN plus the hydronium from water, which we'll call Y, and then I'll have the hydroxide from water, which we'll call Y. I'll drop the units. Maybe I should put the units in. All right. Now, I look at this, you know, the hydronium I'm going to get from water is Y. The hydronium I get from HCN is X. And so here's the hydronium from water. And so hydronium from water we called Y. So this is Y plus X here. It's Y plus X and X. And then the hydronium from HCN we called X. So this is just X plus Y. Do you see the hydronium at equilibrium in both equilibria have to be the same, X plus Y, otherwise we can't get this to work. And so it's got to be, you know, X plus Y at the end, and that way X plus Y satisfies this equilibrium. We could do the double check, and X plus Y satisfies this equilibrium by the double check, and then we're good. And it's the same concentration because it's the same solution. And so this just looks like, two unknowns. If I got two unknowns, I just need two equations because I know what HCN initial is. HCN initial is that. Your book calls this C. That's what your book calls that. And so let's go ahead and generate two equations for this. Two equations, two unknowns. And so I know that Ka for this is 6.10 minus 10. That's going to be the hydronium ion concentration at equilibrium. The hydronium ion concentration at equilibrium is just Y plus X times the cyanide concentration at equilibrium, which is X, divided by the HCN concentration at equilibrium. The HCN concentration at equilibrium, rather than writing HCN initial, I'm just going to write C. C for HCN initial minus X here. And C is a known. And then over here we have KW. You know, KW is 1.0 times 10 minus 14. And that's going to equal the hydronium ion concentration at equilibrium, X plus Y, times the hydroxide ion concentration, Y. And so there we have it. We have two equations and two unknowns. Two equations, two unknowns. Can you go ahead and solve that for me for X and Y? We're good. Let me show you in look. So basically, your book skips the ice tables. The book skips the ice tables, and then we're down to here. We have two equations. The Ka, which is the X plus Y times X, C minus X, and Kw, X plus Y times X. And so we just got to solve that for X or Y by our standard methods. This is for, let's see, what is this for? It shows.